So start sharing the screen. Right, so I think we're recording and sharing the screen. So I'm going to go ahead and download the code. So guys, right? So we are now, we went over a little bit of the theory and background on GPTs, right? And now we're just going to go over the code basically and all the steps, all the concepts. Guys. Okay. All right. So you can just download the code. I'm not going to like type it up, just go through it. So the two things we're going to need right now are the book huckfin.txt. That's we're just basically going to make a Huckfin AI, right? If you want to think of it that way. Some people do Tiny Shakespeare. You may have seen that quite a lot around. And basically that speaks. It's nice to use something like Tiny Shakespeare because you know Shakespeare is very unique. You know, thou has something, you know, or other. So, but in this case, we can use any book. So Huckfin should be fine. You can always just add more books and so on, and you know, do more training. So the idea, remember, is just to train the model from scratch. So this is called the pre-training phase of it, and we're just going to look at all the parts of it. Quite a bit of this is just dealing with the data itself, so the processing of the data, until we arrive at the end. So let's the two files that we're going to need. So we're going to be Huckfin. So I'm going to download this. Okay. Okay, so I'm gonna just download the file. Okay, Huckfin TXT. And then, guys, can you keep it down, please? And then I'm also going to download the Jupyter, basically. There are some concepts where I'm going to use simplified versions of little scripts like the attention, positional encoding, just so that we get a better understanding of how it works. Okay, so let's click on and Caitlin. Right, so I'm going to download the Jupyter there. Okay, so I should have both items now. Guys, please. All right. So I'm gonna click on this one and that one. All right, I'm gonna move them to I think we had a folder for this course. Yeah, this one. Okay, so I'm just gonna create a folder here, GPT. Okay. And I'm going to add the two files. All right, there we are. So these are the two files that we're going to use, basically to try to start to understand and demystify, you know, AI models, etc. All right, so I'm going to start the prompt. I believe I'm sharing this, aren't I? Yeah. All right, so all right, so I'm going to call Anaconda prompt here. All right, dir. I'm going to navigate into the desktop. 520 2024 fall. There, and then we're going to navigate to GPTs. dir. All right, so we have the file, basically the data and the Jupyter. Okay, now I'm going to go ahead and do conda environment list. Any PyTorch should be enough. We don't need any special libraries. All right, so I'm going to do conda activate. Do you guys remember which one I've been using? ML20. Okay. Thank you. Pi38 ML 2024. Great, thank you. All right, so we can start our Jupyter notebook. All right, so here we are, right? So we've talked about basically this is text. This used to be called, it's still called natural language processing. Now it's the term is like LLMs, similar idea. Although this architecture can be used for other things, right? So images, it's not just for text, right? So because at the end of the day, it's just an embedding, and the key thing is to understand how you're representing your data. Okay, so I'm going to go here and just start the Jupyter. All right, so the first part of this, before we get to any of the, we probably won't get to the architecture today. We're just going to start with the data processing, right? So we're going to start reading in the data, looking at examples of how the data works, and then from there, looking at creating tensors from the data, etc. Okay, so I'm going to clear the kernel. Okay. So let's go ahead and start. All right, so this is a GPT from scratch in PyTorch. I'm going to go ahead and run it. Notice the libraries, there's nothing special. We're going to use Torch, NumPy, Torch is NN, and Torch NN functional. So similar ideas, create a model, the architecture, inputs and outputs, and then train with the loss function, basically. We're going to look at some of the parameters here. So there's going to be certain things that should be familiar to you. So for instance, this NM embed, you can see it's that 512 that was in the graph, right? So if you remember that 512, that's just a variable holding that parameter that can be changed. N heads and N layer 6. So basically the number of layers. So in this case, actually the number of decoder layers, whatever you want to call it, there's 6 of them. The number of heads has to do with the attention mechanism. So it's called multi-head attention. You can think of it as you give an input to 8 neural networks, and all 8 neural networks give you an output, and then you just concatenate the results. All right. So in that way, like each of these 8 is producing something different, hopefully, that can be used together. So there's a lot of tricks like that. So anyway, so this parameter is from the graph, that 512 one. This is the attention mechanism. We'll see 8. You've seen that there are 6 layers in the, if I still have that diagram. Yeah, so 1, 2, 3, 4, 5, 6, and this is the 512, basically. Okay, so that's what that is, just defining the initial parameters. Dropout is something that you do in layers to kind of drop some connections. So we just have a dropout there. The vocabulary size, if you look, it's going to be somewhere between 65 and 88. We'll print it out actually. So it's going to be the number of letters to use in this example. Like I said, this is just to make things easier. In reality, you would use something like a specific techniques, something called BPE or tick token, libraries like that, that can literally create IDs and subwords, and then you use that in a second step. But in our step, we're just going to create the letters just so that it's a little bit more clear how it works. Okay. And then, the idea is you can extend this later on. Block size is 40, so I've explained this already as well. If we go back to the graph here, 40 was this input, so it's basically the number of inputs that we can use, the number of words, if you want to think of it that way. Could be the number of letters too, it just depends. Okay, batch size is 64, so batches of 64 sentences all at once. So think of it as, so this is very clever, right? You take the whole book, the whole book goes from 1 to 500,000. I don't know, right? So pick a number, 73. So you start at 73, and then the 40 that follow it, that's a sentence that you slice out, and you use that. Then another number, 8,500, find that ID, find the next 40, slice that out, and that's a sentence. That's how elegant this is, in that, you don't have to worry about a lot of that. You just pick a sentence and then you feed it into your model. So we pick 64 sentences at once in the batch, and we're going to feed the network. Maximum number of iterations, 6,000. At every 500, we'll print the score. The learning rate here is 0.0003, right? So this is we've used learning rates of like 0.001 in our coding examples. Right, and so on. So these are the parameters. Notice here that it says device. This is something that you'll see when we start to look at writing PyTorch code for GPUs. We have to specify the device for the data, the models, etc. This is something that might be a little bit confusing at first, but you just have to kind of be aware of it and then follow examples to make sure that you're doing it correctly. But you'll see that here. So in the previous examples, we didn't have to do that because we were using CPU. Going forward now, as we look at these ResNets, et cetera, throughout the semester, we will have to do this to specify which device we're using. So the nice thing about how this works is, by the way, that PyTorch code will work fine, whether it's for CPU or GPU. So we don't have to do anything different to code for the GPU. That's, really nice. So basically all we have to do is detect if we have a GPU, and if we have a GPU, then we kind of know that going forward, and the code will work on the GPU. If there's no GPU, then it'll run on CPU. Okay. So here you can see device CUDA if Torch CUDA is available, else CPU. So basically it'll do it for you. It'll check that CUDA is installed and everything. And luckily the Scholar GPU devices already have CUDA on them, so you don't have to do anything there. All right, so I'm going to hit run. All right, so I've got the parameters set. Now the next step is to read the book, right? So here I'm just going to, I know my file is called huckfin.txt. I'm going to read it, encoding in UTF-8, and I'm going to assign it to the variable text. And that's it. That's how you read your book. So I'm going to go ahead. Now, length of data in letter or characters, right? So I'm going to print the number of characters in there. And there's about 590,407 characters in HuckFin. Okay? So this is, the number, we're counting just the number of letters in there. List set text just basically should give us the set of all individual characters in this book, right? So if I run that, it basically printed out this, and so it tells me which letters and characters I have in there. K, M, S, C, you know. So this is basically, there's some special characters in there. But this is what we're going to use. So this is equivalent to the vocabulary that you would develop for your own GPT, okay? If we were training something like a GPT-2, this would be, much bigger, okay? And it wouldn't be the words, but it would be like these like syllables, if you want to think of it that way. It's kind of the simplest concept. And we'll touch on that later. All right, so now that I have these, let's go ahead and add a cell here. So this is I have this text. So I'm going to just print text. And you can see there is from the Project Gutenberg, special characters and everything. And then there's the text of, the story of Huckleberry Finn, basically. Okay. So the idea with this machine learning, so if, before we've done classification where we gave it a vector like, a flower, Setosa, and it gave us a class, right? So here the analogy is almost like we give it five words and it gives us the next word. And we have that information. So this is called semi-supervised in the sense that, in supervised learning, you'll take an image and you'll say, oh, there's a cat in there. Or you take another image and you'll say, oh, there's a dog in there, right? That's supervised. In semi-supervised, we have that, but no human had to add that in. All we do is we take a book, and I know from this book, and for modified varieties of, so what comes after that is this, it's in there. So in a sense, you can take the blue part as like the input and the next one as the output. You can think of it that way, right? Make sense? So that's kind of this was not really a thing even like 10 years ago or 15 years ago. Since then, somebody had this really clever idea of, hey, that's semi-supervised. Let's exploit that knowledge somehow, right? And that's where these GPT models come from. So anyway, that's the whole book. Kind of big, so I'm going to comment it out. All right, so now let's take a look at some of these. So I'm going to add a few more cells. I'll break it down. So I want to know what the characters are. So I'm going to take the list, I'm going to sort it, and I'm going to do the characters. And so I have them basically, this is what I need to convert those into IDs. And then I need to take those IDs and create embeddings of them. And then the transformer, as it's training, needs to learn these embeddings, basically. Okay, so I did that part. All right, then I'm going to take the vocabulary size. Actually, the whole thing. I'm just going to run this whole thing. We'll talk. All right, so if you look here, so I have the vocabulary size is important, especially because at the output, we need to define that parameter. So here we take the number of characters, the length of it, which is vocab size, right? And we can print out that value. And it's 88 basically. So that's the vocabulary size. Here, this example just joins all the characters into a string, and you can, for more easier viewing, basically. So you have some numbers, letters. And so what's going to happen is we're going to create a model that is going to learn to create these sequences, right, of values based on not probabilities necessarily, but the weights of the neural network. Based on what it's seen before, it predicts the next one. All right, so the next step is we're going to create dictionaries of strings to numbers and numbers to strings. So what is called usually like the forward dictionary and the reverse dictionary. Okay, so that will be the next step. Okay, so if you look, we have the characters. We're going to enumerate through the characters. And by enumerating, we have the position of it and the character itself, right? So I'm going to just run these. And then I print the dictionaries, and you can see I have a dictionary where, for instance, I have a space, and that's going to be value 1. I have the letter uppercase L, and that's ID 37. You see that, guys? So over here, I have the letter T, and that's number 73. And this other one down here is just a reverse of it, so that in the end, when we start to produce IDs, we can quickly look up the letter that it corresponds to. They're just the same thing in reverse. Okay? So here you can see, for instance, I should give it 71, right? And it's going to give me R. So it'll predict 71, and then I can look up 71 to be an R. Got it? All right, so this is the dictionary for mapping letters to integers and so on. So let's take a look at an example here. We're going to create this function in code, and basically in code, we can give it a word, right? And it's going to give us the equivalent numbers of it so that we can begin the process. So in this case, we're going to take the sheep language. So I'm going to encode that, right? So I'm going to go here, and that gives me 55, 54, 61, 61. Okay, these are the, so now I'm going to take sentences of a specific size, run them through the encoding, and I'm going to have this list of integers, right? And this is going to be the first input into the transform. And then the key thing is that these integers will need to be mapped into embeddings, right? So that's the basic idea. In reverse, I can take the word, I can take, do I have this L somewhere? Oh yeah, sorry. So I have it here, decode, right? So this decode, I'm going to give it 55, 54, 61, 61, which is, you know, the integer. So that should give me back, right? And there you go. So this is just so that we can convert things easily from string to integers, integers to string, as we're going to be taking chunks of Huck Finn, right? The sequence of integers, or sorry, of letters, and converting it into integers that we can fit into the network. Any questions so far? So this is the simplified version of doing this. Obviously, you would use something like tick token or some library to do all of this for you, okay? But this gives you an insight of how to do it from scratch. All right, now, if you notice here, we're going to take the whole text, which is the whole book of Huckleberry Finn. We're going to encode it in the same way that we encode it, and we're going to create basically a list of integers, and then that should be also made into a torch tensor, okay? And then we're just going to assign that as data. So I'm going to go ahead and do that. And there it is. So basically this thing that you see here is the whole book of Huckleberry Finn, but now as a list of integers of the letters in there. Okay, any questions? So remember that, so basically this is how you would have to do it. You would, if you were using syllables or subwords, obviously you'd have to break the text into these subwords and then convert each of those subwords into a sequence of integer name. But that's a little bit more complex process. Any questions? All right. Yeah, please. It's whatever is in the text in there. I have no idea. 0 was, you have to look it up in the, there's probably 3 enters in there at least. So if you look, 0 corresponds to new line character. And so, where is it? So probably you have 3 new line characters in there, at least. Make sense? Did you have a question?
Yeah, so how do we get to characters we have not seen, or do we not look into that?
If we what?
To characters that is not in the dictionary? Like, do we have a special token?
Oh, unknown or something like that. You would have something called unknown.
Like, do we have that here?
I don't have that here. This is super bare bones. So if more robust thing needs a library, probably like something called tick token.
And secondly,
do that.
So essentially here, each token is a character.
Here, in this example, it's a character. So the vocabulary in this example is 88, I think. See, 88. Just a unique letters in Huckleberry Finn itself. But this is just to make it easier, but if you were doing this more appropriately, the best way would be something called subwords, which is like a syllable, but instead of being normal grammar syllables, they would be things that are based on frequency of occurrence, right? So you're going to break up you need to do one pass where you analyze all your text, right? And you need to find in all the text, what are common sequences of letters? Like, Z, H probably doesn't occur that much, but something like SA does occur a lot. So because that's going to occur a lot, it'll probably have a lower number in the ID space and so on. And also it gets selected as one of the subwords to use. So it's all based on a frequency calculation. There's algorithms for that. One of the famous one is called BP byte position encoding or something like that. Can't remember. Byte pair encoding. Okay. But it's a specific set of steps. Yeah. And I have skipped it for this example. So in this case, I'm just doing it from scratch. However, I will say in the other in the link that I gave you, this one, if you go, there's a section called data wrangling, and that does it by words, I think, per words. I just won't have time to cover that probably, but if you're curious about that, yeah, data wrangling from scratch. So you can, this is a bit more robust, and it'll look at, I think, either words and it'll have the unknown and everything like that. So you have to create these dictionaries, basically. So these are all the steps. All right. Okay, so we have our dictionary here, very simple. And the key thing that I want you to understand is we need to, from this, create that n by 40, right? Where it's going to be certain sentences, sequences, and then the IDs that we're going to have in there. And then that needs to be converted into something like n by 40 by 512, the actual tensor that goes in, which is the key thing in the whole GPT. This tensor of n by 40 by 512 is critical. Obviously, you can change that 40 to some other value, which means just be consistent. And the 512 nowadays, 796, 1024. It just depends on your computing power. Okay. Because the bigger the embedding, that's more weights, more processing, just more. All right. So we have the data, right? They have the data. Now we need to figure out how to process it. So here I'm splitting the data by doing a 90% split of it. So I'm just going to take basically, I have the whole book, right, from beginning to end, and I'm going to take 90% of it for training, and I'm going to leave the other 10% for testing if we need to use that later. Okay. Get batch. So this is a kind of a tricky one, but it's really nice how it works. The idea is that we need to take a sentence, basically, that's going to be input and output and just like shift it by one. All right. That's going to be the key concept to understand. Okay. And it's very essential. So here we have get batch. If we want to train or test. So in this case, I'm just going to use train data. We need to select this IX, which is best breaking it up into parts so we can kind of parse it out. So once we have this IX, we're going to iterate through these elements in IX. And if you notice, we're going to create X and Y, where it's going to be from I to I plus block and I plus 1 to I plus 1 plus block. So it's going to be like the same one, just shifted by 1. All right, so that's the critical thing. So 2 steps here. So the first one is we're going to try to understand what this IX gives us. All right, so I'm going to run the function. All right, so let's take a look at what IX is. All right, so that's this one here. We're going to print it out. So we're going to use this function going forward, but in the next few cells, I'm kind of like breaking up each line of code just to see what's going on in there. Also, for visualization purposes, I have made the batch size 4 instead of 40 because 40 then, it'd be harder to see. And I've made, the block size 16 and the batch size. So instead of 32, I think it was, it's 4. And instead of 40, it's 16. Got it? And this is just so for visualization purposes. So we want to select random starting points for the 4 sentences. All right, so we're going to take torch rand int, just like we did here, torch rand int, length of data minus block size. So that just means the size of the whole book, right? The length of it, all right? And then the temp batch size so that we get 4 of those. So if we print IX, that's what we got. Do you see that, guys? Does that make sense? So from the book, what have we chosen? Here we have chosen, think of the book as just one string from 0 to 500,000, I think it was. So we have selected in that sequence 47,693. So we're going to go into that book until 47,693. That's the starting point. And from there, we just grab the next 40 or the next 16. Got it? Then I do the same here. I take 180, 144. So I take 180, 144, and then I just grab the next 40 or 16. That's my other sentence that I'm training on. Then I do the same, 44,397 plus 40 or 16, grab that, and I can slice basically. So it's just like in my book, like here, sorry, this might help. This is my book, so I just pick the ID there, and then I just grab the next 40 of that, or I come to this here, and I grab the next 40 of that, right? So I'm just picking IDs in that book to select. All right. So these are the IDs. So that's why then, once I have that list of IDs, which is this one, I'm just going to iterate through it. So for I and IX, so I'm grabbing each of those IDs, and then that's the ID and the data, and then I just go from the first ID plus block size. And I repeat the same, but just do this +1. Does that make sense? And that's it. That's the magic. That's all you need to do to create your data for training a GPT. Okay? All right. Any questions on this? Pretty important. Homer, so this is kind of just for you. But for the time series thing, then I have a window of like 105 or whatever it is. I just pick one.
Yeah, and then generate.
And then grab the next 20, slice it out, and that one, and the output is just shifted.
Yeah.
+1. That's it. Like that's literally all I'm doing. So and it's random. So if it's 105, I pick one, and then I pick another one, and I pick another one. But once I grab one,
Those are being sequenced.
yeah, grab 20, and keep in mind, since I only grab one, it's always correct because this and the other one is just shifted by 1. That's it. So I wanted you to know that. All right. So anyway, so that's how you give the data, the text data to a GPT model. All right. So let's keep going then, just kind of breaking that function, which we will be using in the future. So here you can see for index temp and IX. Okay. So, and we're just going to print probably like the character and yeah, guys. So here, if you notice, what this is grabbing is at that position, the word that it found or the integer that it found. Got it? So that's what it's giving me here. And then here, as I was saying, where the X and the Y is, it should just be the same thing, but just shifted by 1. So I can go over here and you can see I have my X's there and my Y's. So let's take a look. So this is a batch of 4, right? Batches of 4. Remember that our actual function is batches of 32 or something, but this is batches of 4. And the sequence is of length 16. Got it? All right. So notice over here, on the input side of the GPT is this sentence. On the output side of the GPT is this sentence. Okay? All right. And so now, 145.61, notice here, 45.61. You see that? And then at the end is 82.65.65. Here it's 65.65.1. Just one more. That's it. Homer, and then one less. The other thing, so the ID, instead of learning the embedding, right, this would be the mapping. I just took the actual values, exactly. So instead of having to map 43 to whatever it is, I just put 24 with the values. And that's it. Like everything else, pretty much plain vanilla. All right. Anyway, so yeah, so we have the IDs now. Our next step is going to be to figure out the embeddings, basically. Okay, but hopefully that made sense as far as how the data is created. So these are the batches that are created that we're going to be using for training the GPT. Okay. Any questions on any of that? All right, so it seems like it's pretty clear. This function, estimate loss, this is a function that is just for calculating a performance, like, just like I'm training and I want to see what the performance is like right now. All right, so we're not actually going to be using it right now, so we can skip it, but it's more for performance. All right, so that actually completes the part of processing the data quite a bit. We have our batches, our inputs and our outputs that are going to be fed into the GPT. So that should look, if I go back to the graph, so I'm going to go to the very top of it. It should look like n by 40. I have them now. I have my list of IDs. And so we are ready to feed the data into this n by 40 by 512. Okay, so that's going to be the next part. So let's go back to our script. All right, so this part of the NN architectures, we'll come back to it. So I'm not going to start describing each part. Instead, we're going to look at how, like, the whole big, like the zoomed out version of it. And then we have to drill down into each individual one. But keep in mind that usually in general, N40 by 512 goes in, N40 by 512 comes out. Okay, so the NN architectures are going to be made up of a head section. This head section, if you notice, whenever you see this key query value, that's the attention mechanism. Okay, so attention mechanisms have this key query values. All right, they're nothing more really than projections from one like space to another space of a vector. So we'll take a look at that a little bit later, but that's the head. And then there's something called the multi-head attention, which is actually made up of several head constructs, basically, or classes. Feed forward, this is exactly what we've done before. We're going to need this at some point towards the end of the model. The multi-head attention, as you can see, this uses the head attention. These are the blocks. If you notice, the blocks are made up of what? Multi-head attention classes and feed forward classes. And then there's a few mechanisms that provide efficiencies to all neural networks. That is one of the things that we're going to learn about. Some of them are very simple concepts, like something called a residual. This layer norm just means that we're normalizing the data. Okay, so that's basically what it is. And GPT model is the class actually that brings everything together. All right, so we'll start here. Notice that this class has the init function, it'll have the forward function, and it'll have a new function that we probably haven't seen before called generate. As the name implies, what generate does is it invokes forward, and then it starts predicting in a generative fashion. Okay, and this is also common when we're using things like GANs, etc. So if this seems like a lot, and it is, believe me, it's a lot, don't worry about it. Okay, that's kind of what I would say. Don't worry about the other parts. Just start here for now. All right, GPT model. This is the class that we're going to instantiate. Right? Okay, and just keep in mind it'll have an init, a forward, and it'll have this generate that invokes forward, basically. So we're going to have to think a little bit about some of these parts, and so we'll come back to this. So here, if you notice, this should be more familiar to you, right? This is kind of what we've done before. We instantiate GPT model, all right? So I invoke GPT model. It is this class here that inherits NN module. And that becomes my model that I'm going to be using now. So I need to train it first, and then I'll be able to generate with it. Okay, so that's kind of the idea. So model to device just means that we're tying it. If a GPU is available and we have a lot of data, we want to tie it to a GPU, basically. So as I said, if you run this on the GPU code for Scholar, it should work pretty well. The optimizer is going to be torch optim atom. Notice that the parameters of M, which are the weights, get assigned to that optimizer, basically, with this given learning rate. Okay? All right. And this should be the training process. So you can notice this function is actually pretty straightforward to train the GPT, very similar to the previous ones. So let's think a little bit about the logic here. M is the model. The loss, by the way, in this example, it's kind of a little bit different. It's embedded within the model itself. So it should be, if I go to the model, what's the loss? Yeah, it's right here. See the logits, and here it is. That should look familiar to you, right? So it's using the cross entropy loss function, just like we've done before with classification problem. Even, if you remember, I said usually MSE or cross entropy, and here, right there, you can see the loss function is built in. I mean, this code could be written in a different way where the loss function is outside, but it's sort of similar. Okay. All right. So anyway, so let's go back to this idea here. So we instantiate the model, assign it to the device. We have the optimizer. Then we're going to do the training. Okay. So we're going to just iterate, right? So over so many iterations, this is just estimating losses. So you can this is just for printing performance as we're training. Here, though, is the first step. Notice the function I just explained, get batch, right? I just explained this. Remember, what does get batch do of the training set? Go into that book, pick a few IDs randomly, grab each one and slice from there the next 40 or so tokens, bring them out, and then it returns basically batches of that, a batch of 32 of that. And because once you grab a sentence, all you have to do is shift it by one, then you have the input and the output that you're going to need for training. Like you would have an image and its class. So in this case, you have one sentence and its shifted version, input and output. And amazingly, that's how they learn. All right. So get batch gives you XB and YB. So once you have XB and YB, that goes into the model itself, the GPT. Remember that in this case, we usually just give the XB to a model, but we're giving XB and YB because the loss function is in there, right? So this XB and YB, then we can go to the model here. This one, notice forward, it's got IDs and targets. So it's like XB and YB. It's going to go through the whole architecture. We'll describe this later in detail. And then you get the logits here. So this is like the prediction. Okay. That's the predictions after going through all these layers here. That's the whole neural network. And then these logits and the targets right there go into cross entropy to minimize the loss. Does that make sense, guys? Any questions? It's the key aspect here, right? So the model is basically predicting like the next word or the next sequence of words, right? And so though that n by 40 by 80,000, or in our case, n by 40 by 88, right, is what it predicts. And we compare it n by 40 by whatever it is, 88. And that goes into this cross entropy. If it's too different, then the loss is high. If it's close, then it's a lower loss. So this is how the weights are being modified. Questions? Do you see the connection to what we've done before? Questions? Good, clear? All right. Yeah, so again, I'm not getting into all the details, but I want to stress these parts here. So this is the training, basically. So we're going to repeat this so many times. Every iteration, we're grabbing a batch of XB and YB, give it to the model, XB and YB. We go into the model itself here. That XB, which is IDX, this guy over here, if you notice, goes into this. Oops, sorry. Goes into this one. Then that token embedding and positional embedding get added. We'll talk about this and becomes X. That X then goes into blocks, and that becomes X. That X then goes into LNF, becomes X. That X then goes into feed forward head and becomes logits. And that's the prediction that you have. So in a second, I will go back to the graph, describe the graph, and then tie that graph to the code that you see here so we get a better understanding. But once we get these logits then over here, you just have to know if you have targets, then it means you're training. So then you're just going to go ahead and take logits and targets, and there's some kind of a resizing of the tensor, and then logits and targets get compared in cross entropy, right? We measure the similarity, that returns loss, and that loss is returned by the function forward. So now we have to go back to our training here, and if you notice here, we get our logits and our loss. Okay, this loss now is what is going to be used by PyTorch to optimize the weights. Okay, so it's going to optimize through the optimizer and taking loss.backward and optimizer.step. It does the whole calculation of the derivatives and then updating the weights accordingly. All right, remember that's done by Torch, but that's the whole process, and that's how you train the model. So all that remains now is for us to describe that whole set of sequence of steps of IDX going in and being transformed through every layer, including the attention layer, which happens in there. But yeah, that's the overall flow of it. Once you've trained the model, right? Once you've done this iteratively many times, the weights should be optimized. And if you notice, then you should be able to generate. That's it. So if you notice in this script over here, this one, now you can create something called the start of sentence context. It's just going to be a tensor, right? So we have a tensor maybe a 1 by 40 or something like that, right? That we want to start generating. So we just give it the first character and boom, it's going to start generating. But we don't necessarily just have to give it the first, start of sentence. We can give it a question. Who is Huck Finn? And what it does is it'll convert that into, IDs. That goes into generate, and from there, it'll generate the rest. Okay. So that's basically the example here. So imagine here, I'm just starting some tensor to give it some input. You take in that SOS context, m.generate, and you tell it to generate about 500 or so tokens. And then that gives you generated text. And then all you have to do is decode that with your dictionaries. And that's it. You got your chat GPT right there. Not a very smart chat. Okay, but anyway, that's the whole process of this model. This is just me, other examples to play with it. Then here's an example of where is Huck? So just take some sentence, encode it, right? Do some processing. We'll come back to this. And then that new NP becomes the new context, right? And that is fed to mgenerate. And that's equivalent to asking it a question and getting an answer. Like that's in its simplest form, the mechanism, right? Obviously, initially, it's not going to be very good, but there are ways. There's a second set of steps, not something we'll cover in this class, but in the 530 class, I cover something called human reinforcement learning through human feedbacks. And there, you need to learn to align those inputs and those outputs. So there's a whole different process for that. But in this case, we can give it an initial context and have it generate. I didn't mean to do that. All right, so once that's basically it. After that, if you notice, I have these figuring out dimension things. So we'll go over that as well. Some more examples of a lot of it is tensors. So the next thing I want to do is now I've given you the basic logic, right? So now we need to drill down into every single one of these little things. So for instance, I want to go here, the training loop, right? So I do a get batch XBYB. I grab that batch. I grab XB, that's like the text that I'm giving it, n, 40, right, of IDs. It goes into M, which is basically the model itself here. So think of it as it goes into forward, and that XB becomes IDX right there. Okay, so this IDX, if you notice, then you print things like the shapes, B and T. So for instance, the batch is 32, I think. T is 40. But then that IDX goes in to this function, token embedding, becoming token embedding, and something else are added to create X, and X goes into blocks. Then this X goes into LNF, and so on, right? So that's what I'm going to talk about now. So these few lines of code are invoking all of these things: multi-head attention, block, feed forward, head that includes the attention mechanism. Okay, so that's kind of where we're going, and we won't finish this today, but we'll, I want to, we've looked at the big picture now, and now we need to drill down into all these individual areas. So I think the best way to understand this is to go back to the graph, right, and think about it as to what is going on. So I'm going to go back here. So n by 40, right, goes in. That n by 40 will go into a function that converts it into n by 40 by 512. Then the output of that will go into these encoder layers, right? Each individual encoder layer. And the output of that, I should say, I'm looking at the wrong thing also, because remember, we're not using the encoder, it's the decoder. So I'll repeat it. So n by 40 becomes n by 40 by 512. And this n by 40 by 512 goes through these decoder layers. And then the output here, notice that these are decoder layers, but this is called a linear layer. So it'll go through this layer. And then after this layer, it'll go through this layer, the final layer. Okay. So let's keep this diagram in mind, and let's tie it back to the code now and what's going on. Everyone with me? All right. So the first step then is n by 40, right? Needs to go into embedding and positional embedding, two embeddings. So think about this idea, all right? So let's think at the end. We're going to end up with n by 40 by 512. But that n by 40 by 512 is equal to one tensor n by 40 by 512 plus another tensor n by 40 by 512. Equal size, one is the embedding one and one is the positional encoding one, and they just get added together. That's like really like amazing, right? And that's how it works. You could create other tensors that are n40 by 512, like however many you want with other logic in them. And people have tried it, and in general, this works best, like these two. So n by 40 by 512 comes out here, but you calculate two n by 40 by 512 tensors, and one of them is, they're both based kind of on this original input, right? So xb is n by 40 that goes in here. All right, so now let's just focus on these two for now and nothing else. So these two here, let's go back into the code. So should be here, right? GPT model, but actually, let's start here, okay? So XB, YB, XB goes in here, n by 40 goes into the model. This is the model, but we're really focusing on this function here forward, okay? So the first, so that XB is now IDX, n by 40. So IDX shape is just, you can see here, batch 32, comma 40, the integers, okay? And IDs and targets are both going to be batch by number of the sequence, tensors of integers, basically. Now here, this part, notice, this IDX goes into this function. And that's what you get. N by 40 goes in, n by 40 by 512 comes out. That line of code does everything related to embedding. So you don't have to do anything else. That's nice. It makes your life easier because this is actually where the weights are going to be learned so that every ID now has a specific embedding within the transformer. Got it? All right, so that's pretty important, okay? So n by 40 goes in. So what are we using here? We're using something called self-token embedding table. All right, so we want to know what that is. So I'm going to go to the init here. And notice that self.token embedding table is nothing more than the PyTorch nn.embedding. That's it. This is the PyTorch construct to tie IDs to embeddings. That's it. And if you do that, it's like PyTorch knows that as you're giving it data, it needs to learn these weights. It needs to learn that ID 17 should have these values in its embedding of 512 and ID 67 and so on, right? So that's kind of the intuition there. Any questions on that idea? All right, key aspect, as I said, you're gonna get, and the dimensions are pretty important here. So in this case, the vocabulary size, you need to specify the embeddings. That is vocabulary size to n embedding. Why? Every ID in the vocabulary needs to have its own embedding. Do you agree with that? So how many words do we have in our vocabulary? 88, right? Because we have only 88 letters. So there's 88 rows, 512. Right? Do you see that? So we got 17, 512. 88, 512. So now every time that it's almost like a lookup table. I say 3 slices out that vector of 512. But over time, it needs to learn it, right? So this is important because it defines architecture. If the vocabulary was 100,000, it would be 100,000 by 512 and so on. Okay? All right. So hopefully that makes sense. That part then takes care, as I said, of this one over here, right? So now you have one tensor of n by 40 by 512. You have like the mechanism or the pipeline. Obviously, initially, though, the values are random, right? So during training, these weights are going to change until you have a pretty good representation or a pretty good embedding of each of the IDs. Okay? All right. So you have one tensor of size n by 40 by 512. Now you need to create another tensor of n by 40 by 512, which is going to be the positional encoding. This concept actually, to me, I'm sometimes very slow at things, was hard to grasp. Like I had trouble picturing this one, but eventually it's so simple that it's crazy. And this one is what captures the positional encoding. So if you this is important because think before transformers, for many years doing RNNs or whatever, you had to capture this sequence. Like the cat is sleeping on the table. You had to capture that sequence. Now you have a little tensor that just captures the sequence. It's designed basically to capture the sequence in a very clever way. So let's take a look at it. There's actually two methods for this to be done. One is the famous sines and cosines that you may have read about. Maybe some of you have been curious about how positional encoding is done. So there's a sines and cosines version. This is not that. This is another version. Notice that I just aligned these two things and they're both NN embedding. Okay, notice that. So let's take a look over here. So remember, I send XB through M. XB is literally IDX. I send IDX through the embedding table, and now I have my token embedding of size n by 40 by 512. The next step is where I do the positional encoding. So it's this line of code here. Notice that it doesn't even have IDX going through it. Do you see that? This is something that was so weird to me when I first saw it. Why is IDX not going through it if it's like dependent on it? But it's actually like a constant kind of a thing, you'll see that in a minute. So the point is, I create a token embedding of n by 40 by 512 using IDX, and I create a token embedding of n by 40 by 512, which needs to capture the position of the text. And then once I do that, I just take both of them and add them, and that's it. Positional encoding and embeddings then become a one single tensor X of n by 40 by 512. And then from there on, I'm going to use those in, notice, X goes into self.blocks. So if we go back to the diagram, n by 40 by 512 comes out, and blocks, and that blocks that you just saw is just these. So it starts to go into all these blocks to get transformed, okay? Any questions? All right, so now let's dig into the positional encoding part and just kind of see how that works. So let's go here. All right, so notice positional embedding, which is the positional encoding that gets added here, is invoking self-position embedding table. So this is something that we've defined in the init function. Okay, so let's go over there, look for positional embedding table. Here it is. Notice that positional embedding table is nothing more than NN embedding, where we give it block size and we give it an embedding. So effectively, this is a matrix of what size? Should be 40 by 512, correct? Yep, all right, 40 by 512. So then the trick is that we're going to map, we need to map some, in the past, let me say it this way. In the past, I mapped an ID to an embedding. So I mapped like a 17 to a 512 and an 88 to a 512. But now I'm going to map position. So what's the solution here? The IDs here could be what?
Indexes, like position indices.
The position indices, so the sequence of positions, right? And that's it. That's literally the whole process that's going on here. And so now we can see, so we have block size and embedding, right? and that's position table. So now we've created the object and we just need to give it like the data. So before we were giving it the IDs, now notice we use this function called torch a range. So let's just see what that does. So I'm going to grab torch a range and T should be 40. Do you see that? So let's go. I'm going to create a cell here. This should work. The device shouldn't matter. It's just going to take CPU, and this is 40. That's it. Do you guys see that? Right. And what's going to happen is in this particular case, it learns embeddings for position during training. That's what an embedding does, right? So before it learned embeddings for specific IDs in the sequence. In this case, it learns embeddings for position. And oh yeah, go ahead.
In practice, does the sine cosine embeddings work better?
So that's a good question. So what I've heard is that either one works the same. Like this is Facebook uses this, I think, for I want to say Llama 3 or something like that. You can read it up. And but yeah, in the original Baswani paper, they did the sines and cosines thing. But it's also a constant thing. And in this I'm pretty sure it's Facebook. I don't know which model is using it, but from what I've read, they work the same. Given enough data. Any questions, guys? Did you have a question in there?
Yes, but I'll talk later about it.
Yeah. All right. So yeah. So there's two. I do have the sine and cosines example somewhere, so we can cover that one as well later. As far as the code is, but yeah, this is basically the approach for positional encoding. All right. So it just uses the sequence of IDs, and then it's just going to learn in an embedding. So you can see they both have n embedding of 512. But this one was literally like the vocab. This is the sequence of integers. All right. So now, remember the key thing is that both of these produce n by 40 by 512, right? Those two tensors are equal, so they can just be added. And this is what happens here. And that becomes your x. So at that point, you've created a tensor that has the sequence in theory, and the IDs have been converted to the embeddings. So now you proceed to the next step of the process, which is running that tensor through the blocks, through the individual blocks. Okay, so if you notice this X now, and you notice here, this is the architecture. Exactly like that, right? So only those 3 lines of code that you see me highlighting there can constitute everything in the orange, basically. Actually, even this last part. So everything after here, all the way to the end, is just those 3 lines of code that I just highlighted. But obviously, there's a lot more going on in there that we have to like understand, okay? Any questions? All right, so keep in mind, so n by 40 by 512 is what we have here. So let's go back to the code. So this n by 40 by 512, the first thing that happens is it goes into blocks. So we have to understand what blocks is, right? So blocks is some thing, right? It's probably a list of objects is what I would say. So let's take a look, okay? And please raise your hand if you have any questions. So I give it this. So now I need to look up what self.blocks actually means. So here it is. In my init function, I have my self.blocks. So what is it? So there's in general 2 ways of defining the architecture of a deep neural network. One is the one that I use extensively, like I have X, linear 1, X, that X, activation 1, X, X, linear 2, X, activation, and so on. You get what I'm saying, right? One input goes into a function. There's another one called the NN sequential. This one doesn't, it just like creates several constructs, you know, of PyTorch, and you just have to list them, and then your X will go through all of them without you having to do X, go into this function, come out as X, and pass it on. It's like it's two ways of doing things. Okay, so we're running out of time, so I will bring up an example next time in next class where I show you this second approach of creating PyTorch objects. Here, this was chosen because it makes it's convenient, basically. It's pretty convenient. Because what we're gonna do here, if you notice, is create a list, but it's kind of like a pointed list here. So notice what we're doing. So for I or whatever, we're discarding that index in range of n layer, where n layer was probably 6, if I remember correctly, right? So we had 6 layers. What do? That list instantiates 6 blocks. Do you guys see that? So we have an object called block defined somewhere here. This one, right? This class. So we instantiate that class with its corresponding parameters, and we just create 6 of them in that list. And now when we feed that list to blocks, it'll treat them in sequence. And it also takes the X and it goes through the first block, then the second block, then the third block, and so on in that order. It's a second way of doing PyTorch neural network. Okay. So as I said a little later next week, I will start here and give you an example of that just so that you understand why this is. It's just a very efficient and convenient way in like 3 lines of code. Think about it. They're coding this whole thing, these 6 blocks. Get it? Also, we're going to use the NN sequential when we look at convolutional neural networks, because also it just makes it easier to create the objects. Any questions there, guys? All right, so it's 7:38, so I'm going to wrap up soon. Stop here, right? And I'll leave some time for questions, etc. And then just, next class, no class because it's fall break. But after that, we will finish up. We should be able to finish up the rest of the code, right? And, move on to other topics. All right, so just to wrap up here, guys, so we're going to create this object called blocks here. Just keep in mind, this blocks is going to be a list of 6 blocks being used in NN sequential, so that when an X goes through it, it'll go through one block and come out, and then the next block and come out, and so on. All right. Once that happens, that X comes out here, and then it's going to go through LNF. And let's take a look at LNF. So LNF is layer normalization, actually. So it's normalizing the data, not actually like an architecture, but just a normalization. And then this X will go through LM feed forward head. So that head, if you notice, the key aspect is that it goes from N embedding to vocab size. So it'll take your 512 back N by 40 by 512 and output N by 40 by 88 or whatever it is. And remember that that's what it predicts, and it's going to compare to whatever you have there. Got it? All right. So, and that should be the end of it. After that, you get the logits, which is just the actual predictions, basically. Okay. So, yeah, so it's 7:40. Let's stop here today with the code, and I'll pick up next class here on the sequential and go from there. We should be able to finish this in the next class we meet. All right, so I'll stop the recording, and if you have any questions about anything, please let me know.